And next we have number 3. In this one we have this binary operation denoted by this wedge symbol on the set of first 5 positive integers, and the operation is defined by this equation. A wedge B is the minimum of A and B. We have to write the composition table for this operation. So in the composition table, of course, we reserve the first row and first column for the elements themselves. And instead of keeping this cell empty, we write the operation here so that we can know, looking at this table, that it's the operation table or composition table for this operation. And now we are going to fill in these other cells. Note that I have not immediately filled in all the cells. Let's first see what these cells are that I have actually filled in. So what are we doing here? We are writing the minimum of 2 numbers. The minimum of 1 and 1 will come here. This cell corresponds to this column and this row. Alright. So the minimum of 1 and 1 is 1. And the minimum of 1 and 2 is also 1. The minimum of 1 and 3 is also 1. So like that, this row, all these cells have 1 in them. Just like that, the minimum of 2 and 2 is 2. That of 2 and 3 is 2. So these are all 2. And then these are all 3, then 4, then 5. Why did I leave these cells empty? That is because if you look carefully, this is a commutative binary operation. It does not matter whether you consider the minimum of A and B or the minimum of B and A. They are the same, whatever it is. So that is why these other remaining cells will be just these cells if you consider the reflection of this upper triangular part about this diagonal. You reflect this upper triangular part on this diagonal like this. That will be the lower triangular part. And this happens because your operation is commutative. Just try to think of it. This is the minimum of 1 and 2. You reflect this element about this diagonal that comes here. That is actually the minimum of 2 and 1, but that's the same. So that is why once you calculate the upper triangular, you do understand why I am calling it upper triangular. This is a triangle in this square grid, upper triangular part. So that's why once you calculate the upper triangular part in the composition table of a binary operation that is commutative, then you reflect it about the diagonal, you get the lower triangular part. So you only need to calculate this part, the rest is automatically calculated. Now let me just fill in the other cells. So that's how you get your table. And to speed things up even more, you do not have to see cell by cell. What you do is, you first of all, of course, along with the upper triangular part, you calculate the main diagonal cells, 1, 2, 3, 4, 5. And then you have the upper triangular part. In the upper triangular part, say you have this first row consisting entirely of 1. You drop it like this. Okay. Make the first row first column. Make the second row second column. You rotate it as if that row is fixed at this point, and about this point you are rotating it. So you have 1, 2, 2, 2, 2, 1, 2, 2, 2, 2. Like that, to get other cells, you then next consider the third row and you rotate it about the third row, third column entry. 1, 2, 3, 3, 3, 1, 2, 3, 3, 3. Do you see that? Then comes the fourth row, 1, 2, 3, 4, 4. So 1, 2, 3, 4, 4. Do you see this thing? The row that you consider, any one of the available rows, you rotate that, you get the column. Let me see the last one also. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that's the table. Next we have number 4. Here also we have the same set, but this time a different binary operation. Star on this set given by this composition table. There are 3 parts. We have to compute this 2 star 3 star 4 given in 2 different ways, bracketed in 2 different ways. And then we have to also answer if star is commutative, and we have to also compute this product of 2, 3, 4 and 5. Solution part 1. So we first calculate this one. This indicates that, the way we have bracketed this product indicates that we have to first of all calculate 2 star 3, and then with the result we have to take the star of 4. What is 2 star 3 from the table? You see the row of 2 and column of 3. So that corresponds to this cell. So that means 2 star 3 is 1. Similarly, 1 star 4 is 1. So that's how it is 1. And then we have this other one, 2 star 3 star 4. So here first you calculate 3 star 4. 3 and 4 correspond to 1. So that's how you have 2 star 1, and 2 and 1 give you 1. So this one is also 1. Part 2 asks if the operation is commutative, and the answer is yes. To see why, you just see the table, you locate the main diagonal or leading diagonal. There is of course another diagonal, we are not talking about that. This is the leading diagonal. And then you flip the upper triangular part about this diagonal and see if you are getting the lower triangular part as the reflection. One gets reflected above this line, comes here, okay, this is also 1. This one corresponds to this one corresponds to this one corresponds to this one. But instead of seeing like that, you can of course see it more quickly by seeing how the rows get turned into column. The thing that we discussed just now in the previous table. 1, 1, 1, these are all ones in the first row. In the first column also, we have all ones. 1, 2, 1, 2, 1, 1, 2, 1, 2, 1. 1, 1, 3, 1, 1, 1, 1, 3, 1, 1. 1, 2, 1, 4, 1, 1, 2, 1, 4, 1. 1, 1, 1, 1, 5, 1, 1, 1, 1, 5. Okay, so yes, that is why the operation is commutative. You cannot, however, write these things as justification here in the answer. Let me write what you actually have to write as justification. You write the reason like this. From the table we see that A star B equals B star A for any 2 elements A and B in our set, and that is why star is commutative. And in part 3 we have to calculate this product. So first we see what 2 star 3 is. 2 and 3, so that one is 1. Okay, 2 star 3 is 1. And what about 4 star 5? That is also 1. And 1 star 1 is 1. So the answer is 1. Next, number 5. Let star prime be the binary operation on this set. Again, the same set defined by the following equation. This time it's different. A star prime B, A and B of course are coming from this set, is the greatest common divisor of A and B. We have to say if star prime is the same as star, that means this star from exercise 4, justify. And the answer is yes, they are the same. As justification, you have to write something, right? You calculate the composition table for star prime independently without looking at this, and then you see if you are getting the same table. You will see that yes, you are getting the same table. But actually you can just simply check that here itself. Instead of seeing what star is according to this table, what if you apply the GCD definition here, as if you have GCD here as your operation instead of star? What is the greatest common divisor of 1 and 1? 1. In fact, the greatest common divisor of 1 and any other integer is 1 from properties of GCD. So that's how you have this 1, these are also 1, and note that the greatest common divisor function is symmetric. I mean, operation is symmetric. GCD of A and B is the same as GCD of B and A. The order in which we consider the numbers does not matter. What's the GCD of 2 and 2? 2 and 3 are relatively prime. That means there is no common divisor between them except 1 and minus 1. That is why here also the GCD is 1. The GCD of 2 and 4 is 2. 2 and 5 are relatively prime or co-prime. So GCD is 1. Like that, you can verify that yes, actually this is nothing but GCD. So you write this thing yourself. I mean, see, essentially this is what you have to do. You make a table like this where everything will be just this, except here you will have GCD, or you write star prime. And then that's the solution. And then you write, yes, it's the same one.